I found
I'm
it.
not sure.
It's, I think now it is recording, yeah?
Yes.
Yes.
Good. Okay, good morning, everyone. So today's co-host is Rahul. So if you are trying to get into the waiting room, I don't know why I'm saying this because all of you are in already. But if you need to leave for any reason, Rahul will let you back in. Okay, so we have a lot of things to do today. So let me get started. Just an administrative matter. I have already put up yesterday's video lecture. I've also put up a pure audio version in case you just want to hear the audio. I've also put up the PDF of the stuff I was writing. Plus I put 3 other PDFs of other notes that I've made. So one of those notes is called Basic Logic. And it was not written for you. It was written for Comp 330 students 2 years ago who have in general a much weaker math background. And so there's lots of really elementary statements like what does the and symbol mean and stuff like that. What does the curly brackets of set notation mean? But there are a couple of things in there that might be of interest to you. One of them is a section called quantifiers and games, which is a way of understanding alternating quantifiers, which I'm going to start with today. The stuff I did about well-foundedness and induction is also in those notes. So you can give a quick skim. It's 17 pages and it's written in a much more elementary way than is appropriate for this group. But still, I think you can read it fast. And if there are a couple of things that are new to you, well, then you have that. It also mentions basic concepts of what a rigorous proof is like. So things like if you want to prove that P implies Q, you get to assume P, and then using that, you get to try and prove Q. So I'm not going to explain again when people say, hey, why did you get to assume that? I will say, go read the notes. That's if I'm in a good mood. All right. So first thing I want to do today is quantifiers and games. So those of you who are in Math CS will have taken math courses like algebra or analysis or both, in which you will have seen definitions like continuity, uniform continuity, which have quantifiers in them. And you maybe through dint of repetition, you have learned what these things mean and how to process them. But this whole notion of quantifiers gets complicated to understand and internalize when there's a whole sequence of them. And this complexity becomes particularly acute when the universal and existential quantifiers alternate. Now, one crucial thing in reading logical formulas is the exact placement of the quantifiers. This makes a huge difference. So let's say we're talking about numbers, the natural numbers. So my quantifiers, the quantified variables will range over the numbers, and I write down this formula. Okay. And you look at this formula and you say, yeah, of course that's true. And then I can write down this formula. And you look at that formula, and if you think for a little bit, you'll say, no, that's obviously false. But you see, the only difference is the position of the quantifiers has changed, not even the actual quantifiers. They're both cases, the existential is on M, the universal is on N, and the propositional formula following the quantifiers is exactly the same. yet these things mean completely different things. This is true of the natural numbers, and this is false. And what does the first one say? It says, for every integer, I can find another integer that's bigger than it. Yes, sure. Give me any integer, I can add 1 to it, or add 17 to it, or whatever. So there is, it's certainly true. The second says there is some integer such that any integer you find is going to be smaller than the one I picked. And that's obviously not true. That would be saying there's some largest integer that's bigger than everything else. Okay, so that's absolutely not the case in the natural numbers, which, by the way, do not include infinity. But what makes the difference is only the placement of the quantifiers. So when you just have 2 and there's just one alternation, it's kind of easy. But if there are more than 2, it becomes difficult to read and interpret. So the way I'm going to interpret these things is through games. So there's going to be a game with 2 players. And these players have names. One is called Eloise, and the other one is called Abelard. Once I wrote these notes up some years ago, and one of my colleagues said, oh, you should not give them such exotic names. They should be called Esther and Arthur or something. But Eloise and Abelard have some historic significance. So Eloise was the daughter of a rich man in one of the Mediterranean towns on the south coast of France. I've forgotten which one, possibly Marseille. And her father hired Abelard to tutor her in the womanly arts, which in those days apparently included logic. So he invented these games that I'm going to describe to explain to her quantifiers. And that's how these games are known today. Sometimes people say Adam and Eve because those also match nicely with A and E. But I will stick with Eloise and Abelard. Now, when you see a formula, each quantifier represents a move. And the move consists of choose a value for the variable. Okay. And if it's an E, it's Eloise's move. If it's an existential quantifier. And if it's a universal quantifier, it's Abelard's move. Okay. And then at the end, verify whether the proposition with the variables fixed, with the variables taking on the chosen values, is true or not. If it is true, Eloise wins. If it is false, Abelard wins. Okay, so everybody understand the game? So make the moves in the order in which the quantifiers are written. So let's play this game for these 2 formulas. You see in the first formula, Abelard has to play first. So Abelard picks some number, I don't know, 500,000. And Eloise gets, so this is the crucial part. Eloise sees the move Abelard made. So she gets to look at this move and say, okay, now I choose M based on what I saw you do. and she can easily choose an m that's bigger than the n he chose. It's absolutely clear that she's going to win this game. In the second one, she says, I have to choose a number and I don't know what Abelard is going to do. So she just has to pick some number and she has no information to go on. Then Abelard, who now gets to see Eloise's move, gets to say, okay, I'm going to make this false by choosing an n bigger than your m. So clearly in this case, Abelard wins, and this formula turns out to be false with that set of choices. So it's very easy to see that this thing happens. But the point is, you can play this game when there are 75 quantifiers all alternating between exists and for all. And then we have a theorem, and I emphasize this is a theorem, not some vague intuition that I cooked up. It's the theorem. A formula is valid if and only if Eloise has a winning strategy. So this phrase winning strategy is important. It's not just Eloise won because Abelard made a stupid move. Winning strategy means she has a way of reacting to anything Abelard does in a way that's guaranteed to let her win, which is clearly the case in the first example and clearly not the case in the second example. So there's a whole mathematical theory of these two-player games. And there's all kinds of games. There's something you've heard of in economics called, game theory. There's even a course at McGill called algorithmic game theory. But so there are different kinds of games that one can talk about. But the games I have in mind are, I think they're called, I've forgotten what they're called. Anyway, they're games that are used to basically to build models for quantified formulas. And so when I say this is a theorem, it's in the properly formalized notion of these kinds of two-player games. I think these things are called dialogue games because there's a dialogue between Abelard and Eloise where they're both making moves and looking. The crucial thing about the placement of the quantifiers is that they're telling you the order of the moves. And as you can see, that makes a big, big difference. So good. That's kind of what I wanted to say. If anybody has a quick question, you can post it on the chat and Rahul will decide whether it's important enough to ask me. If you like, you can look back. If you've taken, let's say, analysis 1 or something, you can look back at your formal definition of what it means for something to be continuous and think of it in this game term. You can also look back at the definition of uniformly continuous and think of it in the game term, and you can see the difference. Okay, now we come back to automata theory. And yesterday, I introduced what we called deterministic finite automata. So these things had a set of states, a set of transitions. They read letters sequentially from left to right from a word, which was just means sequence of letters. And each time it reads a letter, it makes a move from one state to another, possibly back to the same state. And at the end, when it's finished reading the word, you look at what state it's ended up in. And if it's ended up in a so-called accepting state, then you say the word is accepted, otherwise the word is rejected. There are several homework questions on assignment 1 asking you to design automata for one purpose or the other. We designed one that recognized when binary sequences represented numbers divisible by 3. So today I'm going to pose a different question. So design a machine that accepts strings ending in a pair of A's. Our alphabet, we'll just take it to be AB. Yeah, not actually that difficult. It's very easy to do. But I'm going to do a slightly crazy thing. So I'm going to design a machine, and it won't be the kind of machine I described yesterday. It'll be a new kind of machine. And I want you, so I'm going to have a 3-state machine. And this one is going to be the start state. And on both A and B, it loops back to itself. On A, it goes there. And on another A, it goes there. And this is your accept state. So what a strange machine. What's wrong with this machine?
From the start state, there are 2 transitions for A.
Yeah, that's one thing that's wrong with it.
And also from state Q1, you should be able to go back to state Q0 if you see a B.
There is no option for B in Q1.
There is no option for B in Q1 and no option for anything in Q2. So this is a new kind of machine. So it's not a DFA. It's a new kind of machine. We're going to call it a non-deterministic finite automaton. Okay, affectionately called an NFA in contrast with the DFA. So let's enumerate the differences. There can be multiple next states. Or no next state. So this machine makes choices. So how does it work? Well, let's say it's reading a word. So these machines, unlike our DFAs, are very dumb machines. They're programmed in this very simple way. They're finite memory. They have some finite set of rules. They read the symbol. They follow the rules. There's nothing they can do about it. These machines are clever. They get to make choices. And not only are they clever, they have supernatural powers. So this machine is reading the word and suddenly it says, ooh, I think these are going to be the last 2 A's. So instead of just staying in Q0 as I'm reading A's and B's, it says, I know we're coming to the end of the word and these things are going to be the last 2 letters and they're both going to be A's. And then sure enough, it reads an A and it goes to an accept state. Right? So so you see what happens in a machine like this. You have multiple different computation paths through the machine. In the notes that I've posted on the website, I've described this particular machine and I've shown you all the computation paths for a particular string. So there are multiple computation paths, we will call them. Corresponding to different choices. A word is accepted if there exists a path leading to an accept state. Now, if you look at this particular machine, you see if the word does end in two A's and it does make the right choice of correctly predicting when those last two A's are, it will keep spinning. The earlier A's, it will just stay in Q0, B's, it will just stay in Q0. And then when it hits the last two A's, it will go Q1, Q2, accept. Note also, suppose the machine was successfully able to get to Q2. That's only possible if it ends in exactly two A's, because supposing it has two A's and then there are more letters after that. For example, if you come to Q1 after reading an A and then you read a B, you see there's nowhere to go. We say the machine is jammed, and jammed is equivalent to rejection. Okay, so it's not just that you end up in a non-accept state. If your machine is stuck and there's no move for it, then you say it rejects. You see in Q2 there are no moves at all. So if you've come to Q2 and then you see anything, including another A, you reject. Okay, so this is a crucial point that the only way to accept a string with this machine is if it really does end in two A's. Now you might say, but wait a minute, there are all kinds of things that it might do. It might keep reading those, everything, including the last two A's, and just stay in Q0. And then you think, oh, well, this is a reject. But remember the criterion. Yes, there might be many computations, even for a good word, that don't take you to an accept state, but we don't worry about it. As long as there exists one path, at least one path that takes you to an accept state, you accept. Now this makes your design much simpler. So this is not a very difficult example. If I say, come up with a DFA to do this, it's not at all difficult, but it just shows you with an NFA, it's utterly trivial, right? Because the machine just gets to guess. Right, of course, this is total science fiction. So does everybody understand the concept, which I've not formalized with Greek letters and all, but I am going to do that. But is the intuition of what the NFA does clear and what acceptance mean? Yes? Clear to everyone? Okay. Here is the main result, which we will prove in a few minutes. The language accepted by any NFA is a regular language. i.e., could also have been accepted by a DFA. So, science fiction maybe, but the point is, the science fiction can always be removed and converted into a bona fide real machine. And then a remark, there is even an algorithm to convert an NFA into a DFA. Into an equivalent DFA. Here, equivalent means accepting the same language. So this opens up a whole new world for us, because it says go crazy, use non-determinism as wildly as you like, design the machine, and somewhere you can always write an equivalent DFA, and indeed you don't even have to write it because there are programs that do it. It's an algorithm to do the conversion, and in fact our proof will be, we're going to show you the algorithm, at least in Greek letter form. Okay. I'm going to show you another extension. So we'll call this NFA plus epsilon. So what happens in an NFA plus epsilon machine is that this machine can make transitions without reading an input. Not a jump anywhere. So built into this description of the machine will be certain specific transitions, which we will label with epsilon. And what it says is that if you're in one of these states, there's an epsilon move, you could, if you want, that's one of the choices the machine has, make the jump without waiting for the next symbol. So this gives you apparently even more power, but actually DFAs have the same power as NFAs, which have the same power as NFAs plus epsilon moves. And these are all equivalent to regular languages. Okay. So just as another illustration of the power, I am going to describe an example. So you want to do decimal digits, decimal numbers. So what does a decimal number consist of? It has a plus or minus symbol in front, but this is optional. Then it has a sequence of digits, perhaps empty. Then it has a decimal point. Then it has another sequence of digits. This could be also perhaps empty. But you can't have both of these empty. Because a free floating dot is not a number. Okay, so plus 72.39 is a nice decimal number, and you would like to describe a finite state machine that accepts things like that. It should reject things like this. 2 pluses in a row. It should reject, so this is good, this is bad. It should reject a dot by itself. It should reject things like this. Can't have 2 dots in a row, or this. These are all bad things. So by the way, it should be clear that when I say describe a machine to accept something, it has to accept all the things in that language and reject the things that are not in the language. Making a machine that just accepts everything and say, there, I've done my job, it accepts everything in this language, also lots of other garbage, is not a valid solution. It will earn you precisely 0, because the crucial part of any of these design issues is accepting and rejecting. Okay. If it was just a question of accepting everything, here is a simple machine that accepts everything. I call this the Mickey Mouse machine because it kind of looks like a mouse and it has absolutely no power to tell you anything. It just says to anything except, except. Okay, so accepting the right things, rejecting the wrong things, that's part of the design. Okay, so how are we going to do this? As I've already indicated, yeah, you can design a DFA to do this. It's not that hard. I think it was a homework question in Comp 330, but I have more exciting questions to ask you. But let's design an NFA to do it. So it looks like this. We'll call the first state S0. And then the next state we imaginatively call S1. We label it with all the digits. So this is actually a shorthand for 9 or 10 arrows. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all take you back to S1. And this guy is labeled by epsilon or by plus or by minus. So it might decide spontaneously, I'm going to jump there. Or it might, so this is what makes the plus or minus in front optional. Maybe you have it, maybe you don't. Okay. If you got a plus and you jump here and then you see there's no plus transition coming out of this, the machine will jam and reject. So this is why you know it's going to rule out things with pluses or plus minus in front. So either it has exactly plus or exactly minus or nothing. And that or nothing is handled by this epsilon move. So you see these epsilon moves are very specific transitions. They're not just, hey, at any time I can jump from anywhere to anywhere. No, it's not like that. It's part of the design of the machine. Then we have the decimal point. So if you look at how this is designed, you see that it could be reading some digits, or from S1, it can just go right to S2. So this is why it says those digits in front of the decimal point are possibly an empty sequence. But then, if it's possibly empty, you better make damn sure that there's at least one thing after the decimal point. Okay, so now you can accept. And of course, this is ensuring that there is at least one thing after the decimal point. And then if there is more than one, you're just totally happy to accept it. And you see there's no transition for another plus or a dot or a minus. So any of those other spurious symbols will cause the string to get rejected. We said this could possibly be empty. So we have to account for that possibility. So we're going to say, well, if this thing after the decimal point is empty, then I better guarantee that before the decimal point, I had at least one digit. So now you see, so this gives an alternate branch. So if you follow this branch, that means you had at least one thing before the decimal digit. And of course, if you had many things before the decimal digit, you could be spinning here. And at some point, you decide, that's the last one. You see non-determinism here as well, because on any of these digits, you can either just stay there or jump here if it's the last one. So this thing is doing lots of guessing. It's guessing that there is a leading symbol or not. It's guessing whether this is the last guy before the decimal point or not. And I think after that, it's not doing any more guessing. But also we're exploiting the non-determinism by not putting in any transition for plus, dot, and so on. So basically, this thing does the job. It's an NFA plus epsilon, which accepts the strings we want. Anybody have any pressing questions, Rahul?
Yeah, there was just one question, but someone answered it.
Okay. Good. So this gives you some sense for the power of this thing. It was very easy to do this, actually. Yeah, you can make up a DFA. It's a bit more annoying, but ultimately you can do it. And of course, our theorem says it's not just this example, but you can always do it. But it's a great feeling to just say, if you're the human designing an automaton, you can freely do all this magic and science fiction in the design of the automaton and then invoke some algorithm to convert it into a runnable DFA. Okay. The runnable DFA, by the way, does not use backtracking, because one thing you might think of is we let the thing make choices, and then when it finds that this is a bad choice, it backtracks and tries a different choice, which is, of course, a legitimate way to think about it. But the actual implementation of the DFA doesn't work like that. Okay, time to formalize. So here's the formal definition. So we've got the alphabet fixed. I'm not going to put that into the definition of the NFA. I could have, because you can imagine NFAs over different alphabets, but let's fix some alphabets so that I'm not constantly changing it. So an NFA has 4 things. An NFA is a 4 tuple. So 1 is Q, a finite set of states. 2, Q0, a finite set of start states. And of course, I don't really have to say it's finite because it's obviously finite. So unlike a DFA, which has a unique start state, this thing says, I can choose where to start. So that's one of the choices it has. So multiple start states. 3, accept states, which work just like in a DFA. And 4, the transition relation, which has this type. So it takes a state, it takes a letter of the alphabet, and instead of saying you can go to a state, you have a set of possible states where you could go to next, and that set could be the empty set. So it could be on this letter, there's no transition. Okay, so it takes a state and a letter, and it'll tell you, here are all the places you could go to next. All right. So if the set of places where you could go to next is the empty set, boom, the machine is jammed, the word is rejected. Okay, so for NFA plus epsilon, we have a slightly modified version of 4. So this thing says it has this type. So either it takes a letter from the alphabet or the special symbol epsilon, and then it goes to some set of possible states. So anything that I do for NFAs, I could modify to NFA plus epsilons. And I'm kind of, since you're all sophisticated students, I will leave the corresponding formalization of NFA plus epsilon to you. I'm just going to show you what happens with NFA without epsilon. So NFA without epsilon. I'm going to define, just as I defined little delta star before, which tells you how to react to a word, I'm going to define big delta star, which has type Q cross sigma star 2 to the q. And this is defined by induction. Delta star of a q on the empty word is just q. I'm using the set braces because it's supposed to be a set of states. And this is the slightly more subtle one. Delta star q with a word followed by the letter A is you take the union over all q prime in delta star qw, which by your induction should have already been defined. And then for each one of those q primes in this set, you look at what does delta tell you to do on A, and you take the union of all those things. So you can type check that to make sure you understand it. Okay, so delta star q with a single letter, of course, is the same as delta, but this is what happens if you have longer things. And now I can state the acceptance condition. The language of a non-deterministic automaton N is the set of words such that there exists a q in q0, so it gets to choose a start state. And with that start state, if you look at all the places that W could have taken you, one of those should be an accepting state in F. So the intersection of this set with F should be non-empty. So it doesn't matter if there are 15 different ways to get to 7 different final states. That's just as good as having exactly one path. A lot of people seem to think there should be exactly one path. This is absolutely not the case. Any number of paths, there should be at least one path to an accept state. Okay. All right, so that's the definition of an NFA, and that's what it means to accept. So I guess the next thing I should do is talk about NFA to DFA equivalence. Any question about the acceptance condition? Good. Okay, so because I've been assured by all of you who signed up for this class that you're all super smart, I can skip a lot of details that I would normally do in Comp 330, spelling out every single step of every proof. And I'm going to show you some sketched ideas that you can fill out into a formal proof yourself. I'd like to do some proofs in detail, but not any of these ones. Right, okay. So first theorem is given an NFA N, which consists of a set of states, a set of start states, a set of final states, and a transition relation. There is a DFA, which I'll call M, and little delta, such that the language of N equals the language of M. Proof, sketch. Okay, so why it's a sketch is because I'm basically not going to prove it at all. What I'm going to do is show you how to build M. And I'll leave the details of proving that, yeah, M really works as advertised up to you. It's kind of an easy and not very exciting induction on the length of words, but let's construct M. So the crucial point is this. What you do is you keep track of all the places that you could be. And this you can do in a deterministic way. So the idea, keep track of all places in Q where the machine could be. By the way, this abbreviation M/C stands for machine. So keep track of all places in Q where the machine could be. So this means I'm going to describe the state set of my DFA to be 2 to the Q. By the way, I hope everybody is familiar with this 2 to the Q notation. It means power set of Q, the set of all subsets of Q. Okay, so the set of all subsets, the start state. So remember, a state of my DFA is a set of states of the NFA. So don't get confused by the types. So a state of the DFA is going to be some set. And what set? Well, the natural set is to take all of Q0. So you say, to start with, the NFA could be anything in Q. Then we have to describe F prime. So this is the set of all subsets of Q such that S intersection F is not empty. So this means if you say, oh, I've reached this set of possible places and I see, hey, one of them is actually one of the accept states of the NFA, then you know, aha, I could be in an accept state. And finally, the critical part is the transition function. So the transition function says, I'm in some state S. I'm reading a letter A. Where should I be? So you remember what little s is. It's a state of the DFA. A state of the DFA is actually a set of states of the NFA. So I can legitimately write this. Okay, so don't get confused by this type. This S, little s, is a state of the DFA interpreted as a set of states of the NFA. So take the union of all the Q's in that little s. For each one of those Q's, compute where it would have gone, or all the places that it could have gone with the letter A. So this is going to be a set. So for each one of these, I have a set, and I'm taking the union of all of them. Okay. And now we get to write the favorite sentence of all math professors, especially ones giving classes. It is easy to see, that this works. Okay. So that's my end of proof symbol. Now, just a remark. It is possible to have an exponential blow up. In the number of states. And you might want to see an example like that. I will leave that as an informal exercise for you to do. Give an example of an NFA such that when you convert it to a DFA, it has exponentially many more states. And in fact, the smallest DFA will have exponentially many more states. But sometimes it's not such a bad thing. Okay, so how are we doing? Okay, so now we see. So of course, one should do a modified proof for the case of NFAs with epsilon moves. I'm not going to do that. We define something called epsilon closure to be the places one can get to with an epsilon move. So you have a set of states, and then you say the epsilon closure of that set is for any of these things, where can epsilon take me? So that will give you a slightly bigger set that's called the epsilon closure, and everything that I did before will need an epsilon closure in the right place to make it work for NFA plus epsilon, but it's not conceptually terribly different from what I've already done. Okay, I like this class of smart students because this would be like 2 lectures to get this done in a with a normal group. Maybe we can take a short break and we can have some open discussions. I'm going to go get a glass of water, but I will be back. But when I come back, you can ask me questions if you wish. And we'll resume at 11:45. Oh, okay. So what can we do? I am going to stop sharing. I'm going to gallery view. Anybody have any questions? By the way, is Tyler here?
Yeah, I just added him.
Tyler Kastner. Yes, good, great. And I see we have some new people. Maya, you're not taking this class, right? You're auditing? Okay. Uh-huh. So any questions so far?
Are we going to run through an example from converting from an NFA to a DFA?
No.
Okay, I will Google that.
That-
YouTube, that's friend.
That is a mechanical thing.
Okay,
So I don't want to do mechanical things.
understood.
What I would like to do instead, that was Justine who asked that?
Yeah.
Yeah. So, right. I mean, that's executing an algorithm, right?
Oh yeah, I know. It's just to get your hands dirty. I find it easier to remember after that.
Yes. So I think it's even better to do it yourself.
Well played.
What I will do is I will show you a really cool construction that you would not have believed possible without non-determinism.
Is that when you add them together?
Add what together?
When you add two DFAs together and they actually work like that?
Yeah, we will do stuff like that, but what I want to show you first is even more exciting than that.
Okay, cool. I like it. No spoilers.
No spoilers, no. I want to show you exciting and interesting things. So, I mean, of course, you know, having examples and working through some mechanical things is excellent practice. But these are things I'm going to leave to you because, you know, you've watched me fumbling for a long time. It actually gets quite boring to watch somebody convert an NFA to a DFA.
I can't imagine. That's what I expected.
Yeah, yeah. In fact, there's no reason for you to do it ever in real life because there are algorithms available on the web to do it.
Mm-hmm. Yeah, that's how I feel about matrix multiplication.
Yeah, why on earth did they make us do exams in which we multiplied matrices for fun?
I know, right? Got better stuff to do.
I have a question.
Yes.
The example that we looked at yesterday from the DFA that we discussed, because there was no DFA able to compute it, to check if a word has an equal number of A's and B's.
Yeah.
Can we have an NFA that does that?
No, of course not, because I told you anything that you can do with an NFA, you can do with a DFA.
Oh, right. Yeah, never mind.
If you can do it with an NFA, you could have done it with a DFA.
Yeah.
So this apparent extra power of NFAs is an illusion.
Okay.
It's a nice kind of design ploy because you say, I will just design it as if I had all these extra powers, knowing that I can actually get rid of it. Knowing I can get rid of all these weird things like choice and backtracking and epsilon moves, all can be gotten rid of.
I see.
That being said, if I want to describe parametric constructions, it's sometimes not possible to do. You give me any specific NFA, I can certainly convert that to a specific DFA that does exactly the same job. However, if I want to say I have this generic construction, it's quite difficult to describe those generic constructions by always producing DFAs.
Okay.
And by generic construction, I mean things that correspond to operations on languages. So you say, give me any language, and I do this kind of surgery to the language. That surgery will preserve regularity, right? So now you're not giving me one specific DFA and saying, make me the NFA, you have to say, I have a parametric way of saying any language like this can be converted to another language like that in such a way that regularity is preserved. And quite often for those, it's not really possible to show that whole construction in this parametric way with DFAs. But of course, any single instance can be converted to a DFA. And this is exactly what we're going to do next. It's not yet 11:45, so we will, I will wait.
I had one small question.
Yes, please.
We know that we have an algorithm that converts NFAs into DFAs.
Yeah.
But do we know if it's computationally viable at all?
Well, it might be exponential time, right? Because I told you
Okay.
it is, there are examples that show that the potential exponential blow up actually does happen sometimes. So worst case running time is indeed exponential. So any theoretician will tell you, no, that's not viable. But there's a big difference between what the theoreticians tell you and what's actually true. So this particular algorithm is actually used in practice because DFAs and NFAs are used in practice. They are the front ends of compilers. And that's why there are tools that people have implemented. And for any kind of NFA that people write in nature, the algorithm works efficiently in practice. Does that answer your question?
Yeah, thank you.
Can I get some feedback about the pace? Is it too slow?
No, not too slow.
Too fast?
No,
Not too fast either.
no, I don't think so.
And Adam is happy with the pace, whoever Adam might be. Okay. Might get a bit faster in the next half of this lecture.
That's fine. I love a challenge.
I liked yesterday's pace.
Yeah, and today's is different.
I feel like it's a bit slower, but it could just be me.
And who are you?
Omar.
Omar. Omar thinks I'm going too slow. Okay.
We could vote on it. There's like a voting option.
Yes, I'm not that interested in voting on it. I just wanted some feedback. So approximately, what's this? Rahul put the music on. You've got the power. You want background music? Have you heard this song, by the way, Justine, called You've Got the Power?
Yeah, that's a good one.
Yes. Did anybody manage to check the recording quality? Because I put the video up from yesterday. Maya, do you know where to find yesterday's video?
Yeah, I watched it and it was fine.
Okay, good, great. So you're working with Martin.
Yeah.
What are you doing?
Well, I'm doing an independent study to with the material of Math 318 and then a project on computability and Turing machines and stuff.
Huh. Okay, so this is highly relevant.
Yeah.
Though I won't get to computability towards the end.
Yeah, well, it's fine.
I did say quarter to 12, so I really should wait because there might be people who are not planning on coming back till quarter to 12. I looked at the list of topics for today and I see I have to do regular expressions and Kleene algebras and all kinds of things. So Kleene algebras may get shortchanged. Some things which end up being really shortchanged, like, I'm rushing through in 10 minutes to tell you all about Kleene algebras, which really should be a lecture on its own. Well, something will have to be like that. But these are all opportunities for you to explore on your own. I think there were no homework questions on Kleene algebras anyway. Oh, that reminds me, did people look at the homework? Which I also put up yesterday. Anna has not looked at the homework. She's waiting to late night, Sunday night to get started. Oh, Anna, you're just like me. That's how I did my homework. Late night, the night before it was due. Okay, 2 minutes to go. Now, somebody wants to come in. Oh no, it's poor Rahul, who's supposed to be our co-host. We lost you, Rahul. Are you back?
Sorry, Professor.
We lost you for a second. Are you back?
Oh.
So are you still co-host or did you lose that when you left?
I lost it. Yeah, my internet stopped working for a second and I got kicked out.
Okay, maybe I make another person co-host for the second half anyway. Any volunteers? Omar.
I can co-host.
Who are you?
Omar.
Omar. That was going to be my choice anyway. Okay, good. So let us see, where is Omar? I'm looking for you on the list of participants. Oh, there you are. And make co-host. Make co-host. Omar is the co-host now.
Sorry, Professor, could I ask a question about the assignment?
Yes.
Okay, I was just looking at question 10.
Can you say your name? Because I don't know.
Marcel.
Sorry?
I'm Marcel.
Marcel, uh-huh. Oh, there you are.
I mean, it's possible I'm just mistaken, but is for question 10, does n have to be like greater than equal to 2?
So what is question 10?
It's like you design an NFA with n states such that, yeah, the shortest string. Because I was like thinking, because with only one state, you have to reject some states and accept some states. So
accept some strings, not states.
Sorry, accept some strings and reject some strings. So I'm thinking it may not be possible because you only have one state. It's either accepting or rejecting.
Correct. So obviously it's more than one state.
So n must be greater than 1.
Yes.
Okay. Okay. Oh, so are we choosing an n, or is this like, are we making an NFA construction that works for all n? Because that's how I interpreted the question. Like it's a schema to create NFAs for any n.
Is that how you interpreted the question?
Yeah. So I guess I maybe put the quantifiers around.
Yeah. What's the? There's this thing, RTFQ. Read the quantifiers.
Okay. All right.
And this particular quantifier is an existential one. So find me one machine.
One machine, okay.
For one n.
Okay.
With that property, which was difficult enough for me to do. It took me ages and ages. Of course, I was in a pub with people making noise all around me, but I eventually got it, but it wasn't so simple. Okay, it's 11:46, let's go. Let me do screen sharing. First, I want to close this down. Close that, yeah. close that. Yep, okay. Screen sharing. iPhone, iPad, share. Okay, screen mirroring, Zoom. Yes, yes. And here we are. Okay, so Justine wanted to see an example of converting an NFA to a DFA, but I think that's not really exciting enough. What I'd rather show you is how to exploit non-determinism to do things that you didn't imagine possible. So let L be a regular language. So that means there's some DFA to accept it. I'm going to define a new language called half L. Half L is defined to be the set of all words such that there exists another word X in sigma star with WX in L and length of W equal to length of X. Okay, so take every word that you can find in L with even length, cut it in exactly half, throw away the second half, and just keep the first half. So the set of words that you get is some new set of words. So prove that this is also a regular language no matter what L was. So you see, this is going to be a schematic construction. I've got to show you how am I going to do this given an arbitrary regular L. Okay, so I'm going to I'm going to assume that S0 F delta recognizes, so we use the word recognizes L, accepts L interchangeably, recognizes L. And we're going to assume that this thing is a DFA, and we will build an NFA for half L. So this is kind of a funky thing, because you're seeing, so look at how this definition goes. It can't be just any old word. Somehow you're looking at this word and all you see is the left half of this word, and somehow you have to guess that there's something else that you can tack on of exactly the same length, such that the whole word is something that the other machine would recognize. So you're only given a piece of the original machine, of the original word. So here is so there's a whole bunch of ideas. So here's one very clever idea, which I didn't come up with, but one of the students in the class came up with as a solution in the first time I asked this question in Comp 330. So her idea was you start with the DFA, and as you're reading W, you go forward, but also as you're reading W, you try to guess what letters you might have been reading and start from one of the accept states and read backwards. And if these two words meet in the middle, then you know, bang, you're there. So that's a brilliant idea. And that's one solution. I will leave it to you to write that up if you want to see that formalized, but I will do a slightly different thing. So the NFA will have the following state. So let me see, did I write this down or do I have to do this off the top of my head? Oh, I brilliantly did not write this down. Okay, very good. So if I screw it up, you'll have to fix it for me. Okay, the state space of the NFA Q will be S cross S cross 2 to the S. Is that right? Yeah, S cross 2 to the S. So it's going to be triples of states. All right. So the first state, so what this thing is going to do is kind of run a simulation of the machine of the DFA. So in the first thing, this will be used to run a simulation of the DFA as it is reading W. The second state is guess where DFA will be when W ends. And the third thing is track X. So X is the hidden part, the right half of the word that you're not seeing. So you have to guess what could those letters be. I don't know, but it could be any of these things. So I have to guess where I might find myself for any possible letter. Okay, so that's the state space. The start states of my NFA, so they're going to be triples. A start will be, it will be the set of all triples like this. So it's going to be, obviously, the first thing where I'm simulating the DFA reading W has to start with S0. Then I'm guessing that W will end and hence X will start in some other state S. And since that's what I'm guessing, I'm starting my simulation also in the singleton S. And then the final states will be, okay, this S0 will have advanced. It better match up. This second one is never going to change. It's going to be always remembering. Is a recording happening? Yes. It's always going to be remembering where it guessed that W would end. So at the end, we get to verify, oh yes, this is where W ended. And indeed, it's correctly guessed that that's where W ended. And now this thing is going to have to be some state, some set of states X such that X intersection F is not empty. So you get the idea. So I have to tell you the transitions. So delta, so remember what a state is, it's a triple. So it's some S, it's some S bar, that's the state that we guessed where W is going to end, that never is altered. And then there's some set of states which I'll call X. And then I'm going to read some letter A. And then there's a set of possible states to which I could go. So what do those states look like? There will be S prime, S bar, and X prime, where delta S A equals S prime. Okay, so that means the very first state is simply tracking the transition as it's reading the letter of W. But then X prime, I'm not going to formalize this too much, is the set of states the DFA can reach from X reading any symbol. Okay, so you're just guessing any letter from X, you're keeping track of all of them, and you're seeing all the places you could get to. Okay, so there you are. If you get to one of these except states, what must have happened? It must be that for some choice of letters, you did wind up in the final state, and it must be that that word started out exactly where the half that you read did end, and the composite thing is indeed ending up in an except state of the original DFA. So it has to be part of the language L. So this is showing you exploiting non-determinism heavily, how to get left half of L and show that that's always regular. Okay, so on your assignment, I've asked you 2 questions along these lines. One of them is not so difficult, especially if you understood this and formalize it, and that is middle thirds. So I take a regular language L, I take all the words whose length is divisible by 3, I divide it into 3 equal portions, I throw away the left portion, I throw away the right portion, and I only keep the middle. So prove that that's regular. So there's all kinds of matching things that you have to do. Guess where this one ends, guess where that one ends, etc. Okay, so, but it's along the same lines as I did for left half. Much, much more challenging, and I'm sure none of you can do it. Ha, that's a challenge. Is the one that says, I think it's question 7. You take the word, you break it into 2, you take a regular language L, you take a word in L with the following property. It can be broken into 2 pieces. So the first piece has length that is the log of the length of the second piece, or perhaps better way of saying it, the second piece has length that is exponential in the length of the first piece. So you break off a tiny little piece in front, and you've got this whole big piece that you haven't read. And so now prove that this thing is regular. And this is very tricky because in this left half case, we could say for each letter we're reading, we know that there's one letter that we're guessing, and we kind of go in parallel. But with this log, you say the first time I have to match it with 1 letter, the second time I have to match it with 2, the third time I have to match it with 4, the fourth time I have to match it with 8. And so it's an increasing number of letters that you have to match every time. How on earth are you going to do that? So give it a shot. Probably it's one of those things you can find on the internet, but I will personally question anybody who proposes a solution. Okay, so any questions about this particular construction? Because it is quite an interesting one. Who's the official monitor? Is that Omar?
We didn't choose one, but I could do it, I guess. There aren't any new comments.
All right, very good. Let's go. Okay, so that's left half. Very, very important construction. And it gives us an entree into the following, which is closure properties. Of regular languages. Okay, so if L1 is a regular language and L2 is a regular language, then L1 intersection L2 is regular. Okay, so again, because you're also good, I can just do this with a hand waving thing without writing anything down. So what do? You define a new machine. This one, in fact, you can go from DFAs to DFAs. So you've got a DFA for L1, you've got a DFA for L2, you define a new machine whose state space is the Cartesian product of the state spaces of the 2 other machines, of the 2 machines you were given. On every letter, the first component of the product state follows the transition of the first machine, and the second component follows the transitions of the second machine. So basically, you're simulating the 2 DFAs in parallel, and then you check, did both of them end up in accept states? Easy to formalize. So this is easy. Okay, so if L1 is regular, then L1 union L2 is regular. And I'm just going to draw a picture to illustrate the proof. So I've got some machine M1 recognizing L1. I've got some machine M2 recognizing L2. And then I make a new machine whose state space is the disjoint union of the state spaces of M1 and M2. The transitions of the M1 piece follow the transitions of M1. The transitions of the M2 piece follow the transitions of M2. And I just have epsilon moves to the start states. So you non-deterministically guess, hey, is this going to be a word from L1 or is it going to be a word from L2? And then you just go. Okay, so it's also a very easy construction. I'm going to define an operation called concatenation of languages. We've defined concatenation of words. What does it mean to concatenate two languages? It's the set of all words of the form x dot y. So you take a word x from L1, you take a word y from L2, and you stick them together. That composite word is in the concatenated language. So x is in L1, y is in L2. So L1 dot L2 is exactly concatenate a word from L1 and concatenate with a word from L2. Look at the combined word. The set of all such combined words is our concatenated language. So this is also regular. So if L1 is regular and L2 is regular, boom, the concatenation is going to be regular. The proof idea is this picture. So here's the machine M1 that recognizes L1. Here's the start state of M1. So you wander through this machine and then you hit one of the accepting states. Here's the machine for M2. It has its accepting states. So what you do is you go to this machine and you say, where there was an accepting state, I will modify it. I will no longer let it be an accepting state, but instead, what I'll do is I'll put in an epsilon move to the start state of M2. So what is going to happen with this machine? You're going to start with the start state of M1. You're going to read something. If you hit an accepting state, you get the choice of jumping to the start state of M2 and carrying on from there. So clearly, if you do have a word of this form, there is going to be some path that actually gets you there. Slightly trickier is to argue that if this machine accepts something if this machine accepts something, that word can always be decomposed like this. Okay, so I'm not, all these things should really be proved rigorously, but I'm assuming that these things are simple enough that you can just see from this picture how to formalize all this. There are other closure conditions too. These are the really important ones, but here is the most important one. And this one says, I'm going to define a new thing called the star of a language. If L is a language, L star is a new language. It consists of where each of these words is an L, or the empty word might have already been an L. So L star means take a word from L, then take another word from L, then take another word from L, as many as you like, maybe 1, maybe 2, maybe 17, maybe 35, and concatenate them all together, maybe 0, so that would be the empty word, and you get this language L star. This is a very, 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 very important operation in the theory of regular languages. It's called the Kleene star operator. So is everybody clear about how Kleene star works? L might or might not have epsilon in it, but L star always does. Okay, so here's Kleene star, and here's the claim. If L is regular, L star is also regular. By the way, it's absolutely not true, in case you were wondering. If L star is regular, does it mean that L must have been regular? Definitely not. But if L is regular, L star is guaranteed to be regular. And this proof is another little picture, which I'm going to draw with some care. And it looks like this. So L is regular, right? So it has in fact, an NFA to recognize it. Without loss of generality, we're going to assume it's an NFA plus epsilon, and we're going to assume that actually there's only one accept state. That's because what would normally be all the different accept states, we just say, if you reach one of these, epsilon move to our new accept state. So that without loss of generality, once I've got an NFA plus epsilon, I can just say you've only got one accept state. So here is your unique start state. And here is your unique accept state. And here is your machine M1 recognizing L. So what I'm going to do is I'm going to put an epsilon move back from your accept state to your start state. So you see, you've got a word in L, now you get to jump back and try again and get another word from L. So you can do this as many times as you like. And so my new machine has this thing added in. It has an epsilon move to the start state of M1. It has its own new accept state. And I'll put in epsilon move like that. And just to make sure, I've also put an epsilon move just to ensure that epsilon is in the language L star. Okay, so this epsilon move back to the start means I get to repeat this as many times as I want. Again, you should show that anything accepted by this really is an L star. So this is actually a very important construction. It's at the heart of the algebraic theory of irregular languages, this notion of the star operation and its equational axiomatization. So just for your entertainment, I will mention another closure condition, which is not that important. But it's called the shuffle. So some of you who took Comp 302 from me may remember this operation called shuffle. So shuffle says, it's a word that looks like this. Okay, so it consists of words that can be broken down into 2K different pieces. Okay, X1, Y1, X2, Y2. Because there's an X and a Y, it's 2K. So 2K different pieces. If I just take the X pieces, I'll get something in L1. If I just take the Y pieces, I'll get something in L2. And the claim is that if L1 and L2 are regular, then this thing is also regular. So this is not so important for the normal theory of automata, but it's an entertaining thing, and it has some applications in other places, like in the theory of concurrency. But you can kind of imagine how this thing works. You have a machine for L1, you have a machine for L2, and you just put epsilon moves back and forth so that you read for a bit in L1, in the machine M1 for L1, and you say, hey, I'm jumping to the other machine now, and I'm going to read a bit from there, then I'm going to jump back. So you just put epsilon moves back and forth between every pair of corresponding states, and there you are. It's a bit trickier than what I just said. You have to make sure that everything is accounted for properly, but it's not much trickier. But just to give you an idea of the kinds of things you can do with non-determinism. And it really is magic that, yes, you can do all these things with non-determinism, but in the end, you can determinize it. Okay. So here we are ready for a bit of algebra. So these are called the algebra of regular languages. So first I'm going to define a notation called regular expressions. I just want to check something because I'm looking with some alarm at the clock, and I want to okay, so if I don't manage to make it to cleaning algebras today, I will do that tomorrow, and then I'll probably have to push some material onto Friday, but the pumping lemma won't take us 2.5 hours. Okay, good. So I'm going to first define a pure notation, and then I'm going to interpret it. Okay, so this is just notation for describing regular languages. Languages in a machine-independent way. So let me describe the notation. So it's an inductive definition. So I'll just say this is a regular expression. And I'll use regexp as short for writing regular expression. So the empty set symbol is a regular expression. Epsilon is a regular expression. Okay. And then if R1 and R2 are regular expressions, R1 plus R2, R1 dot R2 are regular expressions. If R is a regular expression, R star is a regexp. So some of you may have seen something called Unix regular expressions, which are somewhat richer than this. Have I forgotten anything? So you see, we don't have something for intersection in the language of regular expressions, but we could easily add it. We don't have something for, yeah, let's add complement. So now you see that I've got complement. Of course, this is just notation. Right now, these are meaningless symbols. Oh, and I forgot one very, very, very important case. If A belongs to sigma, then A is a regular expression. So above the dashed line are the base cases of the inductive definition. Phi, epsilon, and any one letter alphabet, any one letter from the alphabet is a regular expression. And then these are inductive cases which allow me to build more complex regular expressions. Sometimes you'll see this excluded, sometimes you'll see this included. I included it for fun. I think for the general theory, I'm not going to have it. Okay, but now interpretation. What do these things mean? A regular expression denotes a language. And the interpretation has to be like this. So I will write this double square brackets around this thing to be the set of strings, which I've also been calling words, in the language defined by R, denoted by R. And now I have to give you this explicit definition. So the meaning of this thing that looks like the empty set is the empty set. The meaning of this thing that looks like the empty string is the very short language consisting of the empty string. Please note these are not the same. This is not an empty set. This is a set containing one thing. The thing it contains is the empty word. This set contains nothing. This is the one letter thing is also a word, a very short word, but it is a word. The meaning of R1 plus R2 is you take the meaning of R1 and you take the union with R2. So just set theoretic union. R1 concatenated with R2. Well, I defined concatenation before. For sets, you just extend it from words to sets by taking one thing from R1, one thing from R2, sticking it together. And the meaning of R star is the meaning of R, and you apply the Kleene star operation to it as described above. And just for completeness, the meaning of R bar is the meaning of R set theoretic complement. So examples. So what's in this language? Well, AA, also epsilon, B, AAB, BBAAB. Nobody said you have to pick this guy first. So you see, these regular expressions don't say anything about machines and recognizing. There's just kind of a notation for describing regular expressions. They're very, very useful. There are all kinds of computer programs that look at regular expressions and do regular expression pattern matching. So you can specify a regular expression and say, find me in this piece of text anywhere where there's something matching this regular expression. And why do we care about these things? A language is regular if and only if it can be described by a regular expression. I mean, you knew something like this had to be true. Otherwise, why on earth did we call them regular expressions? but it's beautiful now. We have this purely algebraic thing, which says here is this family of languages described by these simple algebraic rules. There's a nice equational theory of these regular languages, and they correspond exactly to our machine models given by NFAs. So this thing is often called the Kleene theorem. It's a bit silly to call it the Kleene theorem because he proved so many theorems. But for some reason, the name has stuck with this one. Okay, so it's easy to see that if a language is described by a regular expression, it must be regular. Why is it easy to see? Because we already showed the relevant closure properties. To deal with the inductive cases. And what about those base cases? Well, we have to somehow show that the empty language is regular. That's super easy. Define a machine with A transition back to itself, B transition back to itself, and no accepting states, and that's it. It's not going to accept anything. How do we describe a machine that accepts only the empty string? Well, you make the start state accept, then you make A and B take you to another state, which is not accept. And that state, you just cycle on A's and B's and you just stay there. It's not accepting anything unless you didn't leave the start state. So that's certainly regular. How do I make the one letter language? How do I make a DFA for the one letter language? Yes, you have one transition to an accept state. After that, anything else takes you to some state that's certainly not accept, and you just stay there thereafter. So easy to see that these three base cases correspond to languages that could be recognized by a DFA. All these other things are exactly the inductive constructions we've already done. If I've got machines for R1 and R2, I know how to do the machine for the union. If I have machines for R1 and R2, I know how to construct the machine that does the concatenation. For the Kleene closure, I know how to do that. That was the last of the things I did. Set complement, I actually didn't do, did I? So tell me how to do set complement. Anyone want to tell me how to do? I've got a DFA to recognize L. How do I recognize the complement?
You reverse the acceptance and rejectance states.
Exactly, so it's totally simple. Okay, so if a language is described by a regular expression, whether in this extended sense or not, boom, it's certainly regular. Reverse direction, not so easy. Not so easy. And maybe I will come to it later. Okay, so reverse direction. Later, if ever. Haha. But basically, there's a systematic way of starting from a DFA and constructing a regular expression describing it. And so if you go through that construction, you will see that every DFA can be converted into a regular expression. So if I have time, I'll do it. If not, Google will tell you. what I want to do is say a little bit now about, but even if I'm not showing you that proof, this fact is super important, that there's this purely algebraic machine independent way of describing what is meant by regular languages, and it corresponds faithfully to the description we gave in terms of recognition by automata. The fact that there is this rich algebra, is what makes many questions about regular languages tractable. And exactly the fact that we don't have such a nice algebra when we have not regular languages makes many things undecidable. Okay, so first I would like to talk about equations between regular expressions. So what are these equations? Yes.
Sorry, Maria asked, is the regular expression denoting the language unique?
Excellent question. What do you think?
I think it is.
You think it is?
Perhaps not.
Well, if the expression, so sorry, if I understood correctly, you're asking, is the regular expression denoting a language unique? Yes?
Yes.
If that was true, could we possibly have interesting equations?
No.
No, right? So you see what I'm about to do is exactly tell you that this is not unique by showing you equations that must be true.
Okay.
So for example, let's say our alphabet is A, B. So here's an equation. What does it mean to say I have an equation? It means this regular expression denotes exactly the same language as that one. So just out of curiosity, does this look obvious to you or does it look mysterious, this particular equation? So this is an example.
It makes, I don't know.
Right. I would say this is a not so obvious one. So if you look at this, A plus B star, it says, keep going at every step, pick an A or a B. So I can pretty much make anything, right?
Yeah.
I can make any word, including possibly the empty word, because star says, if you don't want to pick anything, don't pick anything. Okay, so I can get any old word from this. That should be clear. Right, because this is repeat what's inside this. And inside this, it says pick an A or a B. So at every step, I can pick an A or a B, and I can get anything I want. Well, what does this thing say? It says, So you take an arbitrary word. You can always break it into blocks delimited by B. Okay, so what you do is you go from right to left, and every time you see B, you say end of the block. Yeah? Then you start a new block and you go and say end of the block as soon as you see another B. Now it might be that you see a whole bunch of Bs one after the other, so each one of them is its own little block. All right, so what we're saying is you take a word consisting of whatever you like, A's and B's chosen as you want. You can always break it up into blocks, and in each block you have a bunch of A's and then exactly one B, then a bunch of A's and exactly one B. But I've just described to you how you can do that, because what you do is you start from the left end, and as soon as you see a B, you stop. Maybe B is the first thing, so then you stop. All right, so you've got these blocks. What do these blocks look like? Well, in each block, there is a bunch of A's. How many A's? 0 or more. So a block, because remember, A star means 0 or more.
Yeah.
So a block with just a B is got 0 A's in front. Maybe there were 577 A's and then a B. Well, that's also an A star. So it just shows that anything like this could also have been written like that. And then, of course, the outer star says, and then you can have as many of these blocks as you want. So this is an example of a non-trivial equation between regular expressions. And how did I prove it? I proved it by analyzing the meaning of these expressions as sets of strings and showing how you could break up a string, but it was not completely obvious that you could do that.
There's a question from Asa.
Yeah.
Says, does the right side recognize B? Just sorry, an expression with no B.
Does it recognize an expression with no B? That's a good point. No, so sorry, so this is not correct. It needs to have yeah.
He says maybe like add the A star.
Yeah, I think you have to add A star in front of it. To give you the possibility of a thing with no B's. Correct, very good. So even less obvious than we thought. So what I'd like to say is that we have a set of equational axioms for reasoning about equality of regular expressions. And this set of equational axioms is what we mean by the algebra of regular expressions. So you think of regular expressions themselves as being an abstract algebra. The terms are constructed as I described above. So let's leave out the negation thing.
Sorry. Apparently, also, if you have BA. Sorry, one sec. Yeah, a word ending in like BA, then it still doesn't work.
Yes, that is correct. So how does, I'm not remembering this correctly. A star B.
I mean, could you replace like the just have the inner bracket and just have the inner bracket be A star plus B, and then or I mean, there's another one that people suggested. It was you put it.
Sorry, what
before?
Somebody said you couldn't have BA?
Yes.
But you can certainly have BA, right?
Something.
Oh, you'd need BAB. Mm-hmm.
I think people mean you have to move the A star to the back of the A star B star.
So you're saying A star, B star, and then another A star here?
Yeah.
I think that makes more sense, actually.
Okay, yeah.
But this is not the expression I'm remembering. So what is the...
Stefan also said just put a star on the B. It should work.
Yes, but that's not a very exciting one, is it? That's a... I wanted a non-obvious equation. Anyway, let me get on with the equational axioms. So you have a bunch of equations for reasoning about regular expressions. And what do these equations say? So they say that basically um, let us use reg to be the set of regular expressions. Without complementation. And then reg, empty set, and plus forms a commutative monoid. Reg epsilon dot forms another monoid. This one is not commutative. So you see a bunch of different structures, and then dot distributes over plus on both sides. Then empty set annihilates with dot. What this means is that if I take empty set dot alpha, where alpha is any regular expression, this is equal to alpha dot empty set, empty set. So it behaves like 0 does with respect to multiplication. The epsilon behaves like the unit for multiplication. Then we have some more equations that look like this. Epsilon plus alpha alpha star equals alpha star. And epsilon plus alpha star alpha equals equals alpha star. Now we can define an order relation by saying alpha is less than beta if the set denoting alpha is contained in the set denoting beta. So this thing naturally comes not just with the algebraic operations, but with a partial order. It's obviously a partial order because set inclusion is a partial order. And now we have two more rules. So this says beta plus alpha gamma less than gamma implies alpha star beta is less than gamma. And beta plus gamma alpha less than gamma implies beta alpha star is less than gamma. Okay, so these things are not equations, these are rules. They're rules because they're in the form of implications, and they are stated in terms of inequations. We have to state these two similar looking rules simply because concatenation is not commutative. So here is a major theorem, which I'm not going to prove. These rules are complete, i.e., every valid equation can be derived from these rules. But just a remark. In order to do anything algorithmic, regular expressions are horrible, use DFA. Okay, so it's always best to say, go to the DFA and use whatever algorithms you have in mind to work with those DFA. So in particular, if I give you a random equality, yeah, it's absolutely true that you can derive it from these equations, but having an algorithm based on these equations is extremely painful. And one would actually much prefer to use DFA to give you algorithm for reasoning about equality of regular expressions. Anna, you have a suspicious look. No? You believe this remark? Okay, good. So let's see, what are the equations? Here is the equation that I should have written. A plus B star equals A star, B A star, not A B star. Equals A star B star A star. So these are examples of equations. But I've written it as if it's only valid for a choice of A and B, but in fact, it's much more general. It works like this. For any regular expressions alpha and beta, so you can substitute anything you want in there and you'll still get a valid equation. Okay, let me see. How are we doing on time? I don't think I want to throw Kleene algebras at you in 10 minutes. So I'm going to do something else. Let's start off tomorrow with Kleene algebras. So let me come back to this point that I punted on earlier, which is from DFA to regexp. Okay, so I will again sketch the idea and not spell out details. So what the first thing you do is enumerate states. Of a DFA. So you enumerate them 1, 2, up to K. And then what we're going to do is for every pair of states, we define a family of regular expressions. We define R, I, J, N. Every pair of states, let's say IJ, we define, so this is a regular expression describing all strings that take you from state I, take the DFA from I to J, only traversing states 1 up to N along the way. So this is restriction is crucial, right? So Rij0 means only direct jumps from I to J. And this is easy. You can look at the machine. You can see, is there a letter that takes me from I to J? If not, then this thing is the empty set. If there's a letter A that takes me from I to J, then boom, that's A. I'm not even allowed to stop at I and J along the way. I'm only allowed to go directly from I to J without stopping at any intermediate state. So it's either the empty set or a one-letter thing. Okay, so that's the base case of the construction. And now there's a magic formula. So what we do is we compute Rij n plus 1 from Rijn as follows. So given that we have Rij0, we can then compute Rij1. And then from Rij1, once we know Rij1 for all the state, all the pairs, we can compute Rij2. Okay, so what we do is we keep increasing the n that we're allowed to stop at. And we have to compute Rij for all pairs at every stage. Okay, and in the end, when you're done, then you know for every single pair, what regular expression takes me from this state to that state. And so now you can go back and say, okay, so what regular expression takes me from the start state to each one of the final states, and you just take the plus of all of them. And that regular expression exactly describes what the DFA recognizes. Okay, so in the end, when we get Rijk, we have all strings that go from I to J, with now no restriction because it's allowed to stop at any state between 1 and K. And of course, 1 and K means all the states. So is the client clear? So the only thing you're wondering is, how do I get Rijn plus 1 from Rijn? So it's not just Rijn, I have to know all the R's at level n. So the magic formula is like this. So what has happened? You're allowed to go to a new state labeled n plus 1, which you weren't allowed to use before. Okay, so now you're saying, okay, if I could get from I to J using n, that's still valid. But now I have new possibilities. I can go from R to this new state using my old rules, using my old regular expressions. Once I'm there, I can cycle around and get back to that state as long as I want. Let me write this more clearly here. Okay, so here's the picture. Here you are in state I. Here's this new state that you're allowed to go to. And here's J that you wanted to get to. So you could have gotten there without using this new state, but now you're allowed to use the new state. So these paths are still good, but now I could go here. So you see, that's the first term. I could dance around here as many times as I want, and then I can go there. And those are exactly the 3 terms. Oh, sorry. And one crucial thing I forgot to put here, as many times as I want. So star it. And there you are. So this is an explicit inductive construction for all the RIJs. You see, I need all the other ones as well to do the construction. It's a hugely tedious thing to do this, to do an example like this, but by all means, do one yourself if you like. So you can do one for the machine that recognizes divisibility by 3. You get a monstrous regular expression. So we now know how dangerous it is to ask assignment questions that say, here's a very simple automaton, tell us a regular expression. So one of my former students, who's now a prof in a US university, was teaching automata theory for the first time. And so she drew a very simple little 4-state machine and said, yeah, assignment, write down the regular expression corresponding to this thing. And then the students were struggling and she said, well, and then she tried to do it and it wasn't so simple. So then she looked up a website that does this automatically. You can type in descriptions of automata and it'll output the regular expression. And it was something like 40 different terms. So this is one indication that, yes, this is beautiful algebra, but actually anything algorithmic, it's much better to go through the DFA route. But still, this should convince you that I can convert a DFA to a regular expression. So it proves the second half of Kleini's theorem. So next time I will start with Kleini algebra, which is just I'm going to do a very short description of it. And I will also talk about solving equations. I mean, there's some beautiful stuff happening with Kleini algebra. Anyway, maybe tonight in the watches of the night, I will decide whether I really want to do that or whether I'll go into minimization, because minimization is even more beautiful and it's close to my heart. So I guess it is 12:54, 1 minute before stopping time. So I will say goodbye here. I'll stay on for a few minutes if people want to ask any questions, but that's the official end of the lecture.
Cole Killian had a question. I guess just
Cole,
let you know they can probably ask now.
Do I need to keep the screen sharing on?
It's just a quick notation question. So
Yeah.
there you used plus, and then would that be the same as using like the cup union symbol, or?
The cup union symbol is a symbol in set theory.
Okay.
The plus is the symbol in regular expressions.
All right, great. Thank you.
And we don't use the union symbol because there are other abstract Kleini algebras where the plus does not mean union.
Okay.
Okay. Anyone else? Can we? I'll switch. I'm going to stop sharing. Great. Stop sharing. I'm switching to grid view, gallery view. Well, you're all sitting there staring at me, so please say goodbye.
Bye.
Have more questions.
Thank you.
Thanks, Professor.
Yeah. Thank you. See you tomorrow.
See you tomorrow.
Thank you.
Thank you. Bye.
Bye. How many participants are we down to? 5. Rosie, Anna, Prakash, Marley, and Talis. So Anna, I dragged you out of bed this morning in time for the lecture.
Yes. I woke up.
I'm getting up at 6:30 these days so I can do my hour of Pilates before class starts.
Oh, wow. That's admirable.
Yes, but I was right.
Yeah, I aspire to be that.
An hour of Pilates every morning.
Yeah.
Wait till you're 40. You probably don't need it yet now. Anything interesting happening in the chat?
People are saying bye.
When the prof needs to Google their own homework. Thank you. A star, B star, A star. Wasn't this a midterm question in 520? I see. Marcel wanted to put stars on everywhere. Okay. All right. Dali Swang, what are we waiting for now? Nothing. Go away. I'm chatting with my old friends. That's what we're waiting for.
Great. I'm gonna hop off
Yes,
and get some food. But
Talise is convinced I'm going to tell you some vital secret, so he's sticking on. Okay, guys. Goodbye. I'm going to end the meeting now.
all right. See you tomorrow.
Bye.
Bye.
Bye.